Our time on this planet is filled with arrivals and departures. As every organism enters life, moves about, and finally takes its leave, whole populations are affected. Birth, death, immigration, and emigration are all factors that contribute to the growth and decline of populations.
Population is the group of individuals of the same species living in a certain area at a given time. In this program, you will see how birth and death, as well as immigration and emigration, affect both the size and density of a population. By the end of the program, you will understand the population cycles of many species, including humans. And finally, you will have a glimpse at chaos theory and how it applies to population growth patterns.
So, this is the supposed great fishing spot?
Oh, that's what my dad was telling me. You know that once he caught this great big fish here.
Sounds like a fishy story to me. We need a more scientific way of figuring out the population here. Then maybe we can predict the number of fish in the lake.
Well, actually, I was reading in the chapter that was assigned for homework last night, and it was saying something about how to calculate population growth.
Well, that would help, because I'm calculating zero growth in our fish bucket.
I guess in that case, we can quit fishing for today, and I can get that water sample I need for my brine shrimp experiment. Joelle, could you come over here and give me a hand for a second?
Sure, what do you need?
Well, I'd like you to count out 60 shrimp eggs for beaker A while I finish counting out 60 eggs for beaker B.
Sure. What are you going to do with them when they hatch?
Well, they're going to have to be fed, so beaker A is the one that's only going to be fed once during the 2-week period, and beaker B, they'll get fed every 2 days.
Well, what are you going to feed them?
Actually, all they really need is a couple granules of yeast dissolved into their water.
Really?
Yeah.
So what are you going to do with all this once you get it all?
Well, I'm hoping we can use it in class later to help us analyze some population growths.
Neat.
In order to study population growth, we need some initial information about the population. Cameron and Joelle have been doing some studies on population growth. Cameron, where did you start?
Well, population size was one of the pieces of information we needed, so I started with a population count.
What did you count?
The brine shrimp right here, actually. There were 33 in beaker A and 106 in beaker B as of today.
Very good. How about you, Joelle?
And as of today, there are 14 fish inside one of my aquarium and 16 on the other side.
Now, I noticed that you made a point of saying side 1 and side 2, plus you made a point of saying today. Cameron, you also made a point of saying beaker A, beaker B, and today. Why was that?
The proper definition of population size is the exact number of individuals of a certain species
In the same region at a certain time.
Very good. You know your definition for population size. What next?
I guess next we have to determine if the population size changes over time. There would be 4 factors that could affect population growth.
What are those 4 factors?
Those 4 factors would be mortality, natality, immigration, and emigration.
Very good.
Natality is a positive factor because it describes the number of individuals born into a population. Natality, therefore, increases a population. Mortality is the number of individuals that die, so it's a factor that decreases a population. Immigration is the movement of organisms into a region from another area. This, again, increases the population in that region. And finally, emigration refers to organisms moving out of the area, reducing the population. These four factors, along with the environmental conditions, enable populations to be dynamic systems. These systems interact and exchange energy and matter in the environment. Mathematical formulas are used to analyze these systems.
Air Canada is reaching Mr. Eric Hawk. Mr. Eric Hawk, please contact Air Canada for message.
Let's develop a formula to calculate the change in population size. Now, what variables would we need?
Well, if you added births plus immigration, we'd be adding a lot of new individuals to a population.
Good.
And there's deaths and emigration. Those are the individuals decreasing the population. So if you subtract them from the new individuals, you get the change in population size.
Yeah, right.
So then, delta N, or the change in population size, is equal to births plus immigration minus deaths plus emigration.
Good.
Yeah, and if the number of deaths and emigration is greater than the births and immigration, you'll get a negative number, which means the population is decreasing.
Exactly.
To study populations, so far we have counted the number of individuals in a population, and we have calculated how that can change. Is there any other measurements we can make?
Some populations are more crowded than others.
You mean more dense?
Yeah, I guess so.
Isn't that called population density?
Yes, it is. Does anyone know the definition?
Density is the number of individuals in a certain space.
Right. So the more individuals in a certain space, the more dense it is. We can calculate the density of a population. To do that, we need a formula. D equals N divided by S. D is population density, N is population size, and S is the space in which the population lives. Let's calculate the density for your populations using that formula. Cam, let's start with your brine shrimp.
Okay, so if we took B as an example, it would be 106 divided by 100 milliliters, which would be 1.06 shrimp per milliliter.
Good. How about your fish population, Joel?
The fish population in section 1 of the tank is 21 fish divided by 15 liters, or 1.4 fish per liter.
Very good. Now, population density can change over time. Any ideas what would lead to a change?
Since population density depends on the number of organisms, the factors that affect those organisms would also affect the density.
So you mean births and immigration would increase density, and deaths and emigration would decrease density?
Right. Plus changing the space where the population lives would also affect the density.
And that's a very good point. For example, human development often decreases wildlife habitat, and that leads to an increase of certain population densities. So far, we have talked about natality, mortality, immigration, emigration, and space as affecting the density of a population. We need to take into account two more factors, and that would be whether the population is open or close. How would you categorize your populations?
Well, seeing as the shrimp aren't able to migrate from one beaker to the other one, I'd have to say that this is a closed population.
Okay, how about you, Joel? How would you describe your fish populations?
Okay, the fish can freely move within the tank between the two sides, so I say that they were open populations.
Right. Okay, so then we can say that a closed population is one that is only affected by natality and mortality. Now, an open population is one that is affected by mortality, natality, plus also by immigration and emigration. Cam, do you have the data for your brine shrimp experiment?
Yeah, I wrote it all down in my journal.
Great. Let's use the data from beaker A to plot a graph.
For the first few days, there was not much growth in population size, since the eggs were just hatching and the shrimp were maturing. This is called the lag phase, a period of very little growth. But in the following days, the number of births was high. This is called the growth phase, a period of very fast growth. Then there was a period of no growth. At this point, we figured that the number of shrimp being born was equal to the number dying. This is what is known as the stationary phase. On the following days, the food supply was probably close to being depleted, since there was a sharp decline in the population. Plus, there was a buildup of waste and a lack of oxygen. Soon after that, all the shrimp died. This is the death phase, where deaths exceed births.
Good job, Cam. Now, how about the growth curve for an open population? Does it show the same phases as the one for a closed population?
No, it doesn't show the death phase.
Could you explain the growth curve for an open population?
Some open populations tend to exhibit what is called a sigmoidal growth curve. They show a lag phase and a growth phase, and then the numbers tend to stabilize. This results in an S-shaped curve. Other open populations tend to show cyclical patterns of growth. Population increase is followed by a sharp decrease and then increase again. This pattern repeats. Still, other open populations increase and decrease, but don't have a regular pattern of growth or decline.
Okay, we're getting closer to being able to do some population prediction. What we need to do now is figure out a way to calculate population growth rate.
You mean how quickly or slowly a population is growing over time?
Exactly, and that is expressed as a percentage. The shorthand for it is PG %. Does anyone know the formula?
Population growth rate is the change in population size, or delta N, divided by the total number in the population.
Joelle, I think you are missing one piece of information in there.
Oh yeah, times 100.
Exactly. So now, using this formula, we can calculate the daily growth rate of the shrimp population. Let's calculate the daily growth rate for population A.
Okay, well, between yesterday and today, delta N was negative 2.9, and N was 35.9. So the growth rate would be negative 2.9 divided by 35.9 times 100. Hey, that's negative 8%. Is that right? Can a growth rate really be a negative?
Yes, it can. Now, the question I have for you is, at what phase of the growth curve would you expect this type of result?
Probably the death phase.
Right.
So you mean if I would have used results from the growth phase period of time, my results would have been positive?
Exactly.
If we know the rate of growth, does that mean we can figure out how big the population will get in the future?
Well, yes and no.
What do you mean by that?
Well, let's look at the yes part first. In theory, if none of the factors that affect that population change over the period of time that you're calculating the growth, then yes, you can calculate population growth. We need to use this formula. I is equal to R times N. This is the formula for population increase. R represents the growth rate, and N represents the population size. So this formula then we can use for calculating the increase of a population for one generation after the next.
So we could calculate what a population would be in, let's say, 10 years?
Well, in theory, yes. But remember what I said before. None of the factors affecting that population for those 10 years can change. Now, let's calculate the growth of the shrimp population for 5 days. Let's start from day 5 and go up to day 10. That way we can compare the calculated numbers with the ones that you're going to be predicting. Okay, let's start calculating. Are you finished your calculations?
Yep. The predicted populations for beakers A and B is 78.
And the actual for A is 45.
And the actual number for B is 76. And that's closer to the predicted number for B.
One reason the brine shrimp population in beaker B was closer to the predicted number might have had to do with food. We fed them every 2 days during the entire test period. But the shrimp in A were only fed that once, day 1.
Good analysis. Now, the formula and example we use is very simplistic. Ecologists actually use a more complex formula to do population analysis. They use I equals to R times N times K minus N in brackets divided by K. Let's analyze this formula.
So I is population increase. What's the R?
Well, the R stands for intrinsic rate of natural increase. It represents the difference between birth rates and death rates. And you know what the N stands for, right?
N is population size.
And I remember that K stands for carrying capacity of the environment.
That's right. Do you remember the definition for carrying capacity?
I think carrying capacity is the number of individuals that an environment can support.
That's right. Do you remember the factors that affect the carrying capacity?
Well, predation and competition would be two of them.
Food supply and temperature changes would also affect the carrying capacity.
Yes, you're both right. Now, by including K in the formula, we are taking into account those factors.
So ecologists use this formula to make their population predictions more reliable.
That's right. But now let's move a little bit closer to home. Let's talk about human populations. How many of us are there?
3.
In the world?
It's closer to 6 billion, and it's getting pretty crowded.
It wasn't always so crowded. I've been doing some reading on human population growth, and I found some interesting stuff.
Well, let's see.
For 10,000 years, the human population on Earth was relatively small. But in the last century, there's been a huge increase in the number of people on the planet. This is called exponential growth. The rate of growth is due to a variety of factors, such as improved living conditions, better nutrients, and medical services. Some demographers predict that the human population will continue to increase, reaching approximately 12 billion by the year 2042. 12 billion people. That seems really crowded.
Sooner or later, we're going to hit a limit.
You know, we're probably going to end up running out of food or energy.
Or space.
What about disease? Won't infections spread quicker? Remember the plague? Wasn't one of the main reasons it spread so quick because of overcrowding?
Does that happen again?
Well, first of all, we can't predict population. All we can do is, in a sense, give an estimate or get projected figures of what the population will be in the world or in various countries, given that the existing conditions continue. Population growth in the world is becoming a problem. Some areas it's more acute than in others. For example, everyone is familiar with the fact that China has the largest population. Yes. But in a sense, their rate of growth has been declining because of their effective program in reducing population growth, reducing fertility.
So what are the environmental impacts on these countries that have large number of people?
The problems of this disposal of waste, the problems of food supply and preservation and so on, periodically create epidemics and break down so that they have extremely high mortality rates, yes, particularly infant mortality rates. In Canada, for example, the population growth rate is declined to the point where we're concerned about the aging population, so we have quite a different problem.
What are some of the factors that have led to such high numbers in populations?
The population explosion actually began with the European countries in a time of industrialization and development.
There are almost 6 billion people on Earth. By the year 2042, there could be 12 billion. Certain limiting factors, such as available resources, predation, and competition, keep other species within the carrying capacities of their habitats. For example, if we look at this graph on the pronghorn antelope, we see that the population size fluctuates. Only the animals having characteristics suited to the changing limiting factors within their environment will reproduce successfully. Humans, on the other hand, have been able to modify their environment. Advances in science and technology have allowed human populations to extend their lifespans by decreasing infant mortality and increasing natality. All these factors have resulted in unprecedented numbers of people, a phenomenon not common to other populations in nature. You know, so far it seems that we can predict population growth patterns, but you said yes and no before.
Well, we can predict population growth up to a point, but there are some populations that just don't seem to follow the rules. There's a theory that explains why nature is often unpredictable. It has a really great name. It's called chaos theory.
Sounds like the inside of my locker.
That's not chaos, that's catastrophe.
So, what is this chaos theory anyways?
Well, how about the two of you doing some research on that? What I would like you to do is concentrate on the implications of chaos on population growth and predictions.
Chaos theory explains why it's almost impossible to predict the path of a water droplet on the back of your hand. The droplet is affected by so many factors: the tilt of the hand, hairs on its surface, and even the blood flow under the skin.
So what did you find out about chaos theory?
I found an article on the internet called What is Chaos Theory?
Can you summarize it?
Sure. First, the chaos theory is based on the study of nonlinear systems.
What are nonlinear systems?
Well, they're anything that interact with a lot of different factors that occur in no predictable sequence.
So we could say then that populations are nonlinear systems?
Yeah, because there are all sorts of different factors to include. It's complex, it's nonlinear.
So it's not quite so easy to predict population growth. Abiotic and biotic factors that interact with the organisms could influence the rate of growth.
Yeah, because if any of these factors were changed, then the results could be completely different.
That has a name.
Yeah, it's called the butterfly effect.
If you take a leaf traveling down a stream and try to predict its exact path, there's no way. The tiniest shift in the leaf's position can completely change its course. Even something that might seem unrelated can have an effect. A butterfly flapping its wings might scare a frog that jumps into the water, causing a ripple that moves the leaf. You could have never predicted that this would happen just at the moment when the leaf was passing by, therefore changing its direction.
Right, and its scientific name is sensitivity to initial condition. Now, can we apply chaos theory to population systems?
Yes, populations are very sensitive to initial conditions.
That's right. Any small change in the environmental factors could lead to a completely different outcome from anything that was predicted. This graph shows how sensitive the growth of a population is to the initial conditions. The minute difference of 0.3% in this hypothetical fish population is amplified by other factors as the population grows. Any small changes lead to bigger changes later. This makes it really difficult to predict how a complex system will behave. In a real population, there are so many factors that interact, making really accurate predictions of growth nearly impossible.
Okay, back to our original statement. In order to predict population growth, none of the factors affecting that population can change over time. Is that a realistic expectation?
I don't think so. I mean, what if the weather changes? Like, say there's a dry spell that wipes out all the vegetation.
Or if there's competition or predation.
Exactly. Any of these things would change the rate of growth and affect all our calculations.
So why do ecologists spend all this time studying populations?
Well, it's not impossible to predict population growth. What chaos theory does is it provides an explanation of why some populations don't follow the rules. What we need to do now is talk to an expert on the subject.
Chaos theory provides a very compact and different sort of explanation. It says that we can actually explain the entire range of dynamics that we see, stable, cyclical, and apparently random fluctuations in populations with one compact description, in which the environment is not varying. That is, the explanations that are provided by chaos theory provide a deterministic explanation that doesn't need to take into account environmental variability. The actual variability in the populations is internally generated by the nonlinear interactions that are occurring among individuals. If the principal cause of the fluctuations in the populations is because of varying environmental conditions, then one obvious experiment is to take and try to raise the population that you're studying under relatively controlled conditions, that is, try to remove the source of environmental variability, and observe whether or not you get a subsequent change in dynamics. We start replicate populations at one point in time, and we vary by a small amount the initial conditions of the population, that is, the initial density or the size structure, the age structure of the populations. And then we compare the dynamics of these replicate populations that are started under very, very similar initial conditions as to how those dynamics evolve over time. Do the dynamics remain relatively similar to one another, or do you get dramatic divergence in dynamics? If you get considerable divergence in dynamics, then that would suggest that a possible explanation is underlying chaotic dynamics. Of course, these experiments, although they sound easy to do, when we're dealing with natural populations such as insects, fish populations, birds, mammals, and so on, they're often very, very difficult to actually perform either in natural systems or under controlled laboratory conditions. And that's one of the challenges that faces ecologists to try and test the application of chaos theory to understanding the range of dynamics that we see in natural systems. Two areas that chaos theory might be applied in helping us understand aspects of human population might be in helping us understand how social organizations operate. Another area that might be important is not necessarily studying the human population itself, but the disease organisms that affect human populations.
You know, I kind of wonder if this is really going to be a good spot for us to go fishing. If we did a population count, and that would be N, then we'd need to figure out what the mortality and the natality of this population would be.
And because it's an open population, we need to figure out immigration and emigration. And with that information, we could calculate delta N.
And if we had delta N and N, then we could calculate the population growth. Delta N times 100 divided by N.
Yeah, that would tell us how much the population would be in the future.
You know, I think it's going to take us a really long time to figure out what the population of the fish is going to be.
And we haven't taken chaos theory into account either.
I think if we expect to get any fish at all to eat tonight, we're going to have to go to a fish market.
Our knowledge of population size and growth patterns has application for all of us in our daily lives. Humans harvest other populations for survival. Natural populations of plants and animals provide food, building materials, and sources of energy.
Until recently, the human population of our planet was small, and the harvesting of natural resources was modest. We didn't have a huge impact on the organisms with whom we've shared this space. However, a recent explosion of human numbers and the advanced technologies used to harvest organisms have placed some species in danger of extinction. If we're going to maintain the biodiversity of our planet, it's crucial that we enhance our understanding of population dynamics and management for the sake of all of us and our future.